Hi everyone, and welcome to the Vectric user group meeting. Thanks everyone who's been tuning in for all of these wonderful talks. I have learned so much already, and it's just so great when you get to have all of those light bulbs and hear all of this storytelling by wonderful other CNC users and makers. So thanks everyone who's given a talk and all of the wonderful questions you've brought to us. My name's Sami, and I'm here with Avid CNC. I manage our creative direction and media production. And today I'm here with Cory.
Hi, my name is Cory. I'm Avid CNC's customer experience manager. I get to help people leverage CNC equipment to, help launch a business or a hobby or a product. So really excited to talk about some specific CAM techniques used for machining non-ferrous metals like aluminum and brass.
Yeah, so today we're going to be kind of focusing on toolpaths, particularly for aluminum. Here is the sample part I have machined, and we're going to walk through a couple different, very simple kinds of toolpaths that are very common when machining aluminum. So here's the sample part. And Cory's going to walk us through the toolpath programming, and then we'll be back. Well, first we have a little bit of a presentation to talk about the different variables and the toolpaths, and then we'll be back to walk through the actual machining of it and to answer some of your questions. Cory, have any other thoughts about this presentation before we get going with it?
Yeah, I just, like usual, I'm going to say I'm always thinking about the chips we're asking the machine to create when I'm in the CAM area of the toolpath creation. So whether you are using similar vectors to these or different shaped vectors, I just want you to think about the chips we're asking the machine to create. So put your questions in the chat, and yeah, I look forward to it.
All right, here we go. We'll be back right at the end live, and see you soon.
Well, thank you, Sami, from the future, or I don't know, from the past at this point. I'm not sure.
Well, we're here now, so let's just go ahead and jump into some advanced toolpath strategies for brass and aluminum, which is a material I really do like to work with as an accent or as its own standalone material, depending on what you're trying to do. So we're just going to try to break down some of the basics and make this a little bit easier for you when you go into analyzing your toolpaths and your chips and really looking to refine those. So let's just go ahead and talk about the different variables that you have to consider when you are thinking about setting up your toolpaths here. So if you happen to see the plywood and plastics, these variables are kind of the same knobs that you might reach for to turn and adjust as you're trying to get a really good cut quality, a finish, and efficient as well. So we have to consider our kind of semi-fixed variables. So our material, brass or aluminum in this case, that's a fixed variable because you're going to select that and kind of make some adjustments, change your other variables based on these. So your vectors are also a fixed variable, as that's kind of your end goal, the product that you're trying to make. And then your tooling, I think, is also semi-fixed. You're going to reach for specific tools that are designed to work with these materials. Then you're also going to consider your flexible variables. So these are going to be things that you're going to change and adjust in order to accomplish that clean cut. So we'll think about climb versus conventional, raster versus offset, your feed rates, depth of cut and step over. Your chip evacuation is extremely important here. And your material removal rate. So those are the kinds of things you're going to reach for to make adjustments when you're making your tool paths.
Yeah, that's exactly right. So let's talk about some of these fixed variables like the material. So we're targeting aluminum and brass here. And so let's, really analyze those qualities. And so this is an unforgiving material. And I call it unforgiving because if you don't program it correctly, your likelihood of damaging your tooling or your workpiece is higher than a more forgiving material like MDF or plywood or even some types of plastics, where we're not necessarily going to experience tool breakage if we program it wrong. We're just going to see a reduction in cut quality. And so aluminum and brass both have very consistent properties in the sense that they are a refined material. And so they might have some internal stresses or voids within them based on the type of aluminum and brass that you purchased. But typically they're going to be very consistent throughout the material. They come in sheet, bar, and pipe. And so there's a number of different types of these individual materials. So it's good for us to recognize which type of that material we have. And then we also want to talk about potentially, when it comes to chip evacuation with these specific materials, do we want to add any cutting fluid or compressed air to help encourage those chips from leaving the channel that we're creating?
Yeah, definitely. And so the next thing I might consider are the tools, the specific tools that are going to work best with the materials and the alloys that you've selected. So there's the traditional parts of a router bit you need to consider: the flute type, the diameter, which can affect the probability of deflection. Typically, you might go for an upcut, so it can encourage those chips to be removed. And then oftentimes router bits that are designed for aluminum or non-ferrous metals are going to have a specific coating. Okay, so the router bits that we offer are have a special coating called zirconium nitride, or ZRN coating, that's really exceptional for the tool life and then the performance especially. So the ZRN coating was developed specifically for machining aluminum, but it's really excellent for machining all sorts of non-ferrous metals, and is also recommended for machining things like fiberglass and nylon, and other polymer materials as well. So considering the type of coating on your router bits that you have are definitely going to affect the tool life and the interaction that it makes with this specific type of material and the heat that it creates. So do kind of consider that, and read up on the router bits and the what they're designed to accomplish.
Yeah. And then work holding is really important with these types of materials. And when I think about other tools in the shop, whether it be a table saw, a drill press, a bandsaw, any of those other types of tools, how firmly you hold your work when there is an aggressive cut in a hard material is going to dictate the quality of your cut. And that's the same thing here with using the CNC machine. And so typically with these types of materials, we're going to see work holding with a vise or some other type of pressure fit jig or fixture that allows for us to firmly squeeze that material. Now, one thing to keep in mind when you're squeezing material like this is if you have profile or any type of pocketing that could reduce the strength of your part, as you cut and remove that material, your vise or that pressure jig could actually cause your part to collapse and your cut quality go down. And so make sure you're keeping that in mind when using any type of lateral forces on materials.
Right, and so considering how you will zero or reference set your work offsets, your jig is definitely going to affect that. So do be sure to consider that. Other work holding options are, a simple blue tape on the bottom side of your material, and blue tape on your spoil board or your pressure fit jig if you happen to have a little pocket recess for your brass or your aluminum to sit in. Blue tape and super glue or another kind of adhesive can definitely work. This is going to be a faster setup, but and it could also possibly not necessarily have block the side approach if you're trying to machine on the edges, but it definitely isn't as trustworthy as a vise might be. So there are options here. Another option would be to use metal fasteners, which can also help with allowing approaches from side machining, as well as being a really strong and trustworthy work holding. However, it does kind of take some preparation ahead of time to make sure that you have threaded inserts in your spoil board or something to accept that screw, and to make sure that your machine not going to hit those particular screws with your tool paths. So I definitely think metal fasteners are a really great way to go as well.
Yeah. So let's talk a little bit about the difference between a router and a spindle. And really the big difference is how the power is being delivered to the motor. With a router, we are essentially reducing the current as we slow the RPM. And so that means if you're using a router, the slower your tool RPM, the less power it has. And so when we talk about chip load for aluminum and brass, typically we're going to be in the lower range of our RPM for our cutting tools. And this is one area where I feel a spindle brings a lot of value because of the use of a VFD. We're getting a much less significant drop in power as we reduce our tool RPM.
Yeah, definitely considering the kind of spindle or the kind of router that you have will affect the cut qualities.
Yeah, and we actually just came out with a brand new spindle offering, which allows for an RPM range from 1,000 RPM up to 18,000 RPM, and with a peak horsepower of 8.7 horsepower. And so please send us a note, or we'll put a link in the chat here, and you can check out that product.
Yeah, big spindle. Great. So we're going to go jump into VCarve here in a second. But the kind of common toolpath and operations, we're just trying to break down the most common things that you're going to try to do when you're machining aluminum. So first, it might be surfacing. Oftentimes, you'll get your bar and it might be rough and not necessarily prepped for square for machining. So you might want to square it off yourself. Profile side machining. So when you want to engage the side of the cutter to create your profile, engaging the side of the cutter will really help with the cutting tool life, and because you're approaching laterally, it's not having as much of a step down, it's focusing more on the step over. Also, pocket machining is going to be very common here. A countersink, we're going to kind of approach that too, because oftentimes you're going to be wanting to have holes for machine screws and that sort of thing. So we'll check out the chamfer tool. We'll also do a counter bore and a through hole example as well. So let's just go ahead and jump over to VCarve.
Yeah. All right, let's jump into some toolpaths. Now, these toolpaths are going to be able to be used with both aluminum and brass, and really all non-ferrous metals, right, Sami?
Right, so these high density materials like non-ferrous metals with brass or aluminum or zinc, there's several different ones that are going to have very similar qualities. So these toolpaths are going to be very similar. So the trick is to do some tests and then make those adjustments. But this is a good starting point no matter which one of those materials you have in particular for your project.
Yeah, so what we're going to do is we're going to start here and silence my phone.
Mr. Popular.
We're going to start here. We have what we're going to do here, we're going to start with a 12 by 3 inch blank that is a 1/2 inch tall. And right now we have this zeroing to our machine bed. Sometimes this can be really nice when you're doing surfacing or any other type of facing. And that's because we are surfacing it to an exact height. We know exactly where we're getting to there. So we have a 1/2 inch thick material, lower left-hand corner as our XY datum. Perfect. So we have this set up. And one trick that Sami's taught me here is to draw a vector that's the size of your workpiece, just using your snap tools. We'll go ahead and do a square corner on that. Apply OK. And then we'll go ahead and just set an offset here. And we're going to set this offset outside. And we're just going to go just larger than our tool diameter here. So we're going to go ahead and offset it. And this is actually going to be the vector that we use to surface our piece. Right, Sami?
Exactly. So surfacing is oftentimes the first tool path that we'll do for cleaning up a piece of raw aluminum or even wood as well. This is a really great operation to start with. And I like being able to enter the surfacing from the outside of the material rather than from the inside, and making sure that the material dimension is offset just over that tool diameter is really going to help with that.
Yeah. So we're going to cut down just 0.010 of an inch. So we're just going to go down and surface that top material. This is when surfacing, sometimes you might have to go through a toolpath once, twice, or 3 times, depending on any voids or inconsistency with your material or your work holding technique. And so if you do find that when you're surfacing only half of your material is getting engaged with your tool, your work holding might actually be holding your material blank at an angle to the gantry. So we're going to do a cut depth of 10 thousandths, so we're just going to barely kiss this material. Let's go ahead and hop into our tooling selection area. This is a great time, continue to make new tool parameters as you go through these different materials and types of tool paths. Some people like to use spreadsheets. I really like to modify my tool database and have that information in my database, so the next time I come and go to that material or that type of tool path, it's right where I need it to be. So we're going to select our ZRN upcut tool. Right now we have this set up at 20,000 RPM and 100 IPM. So this is giving us a chip load of just over 2.5 thousandths thick. Go apply and select. It has a 40% step over. And we're going to go ahead and do a raster cut here. And so with a raster, we're going to do our profile, no profile cut. And what we do want to do is we want to make sure we know where our starting point is. So let's go ahead and select this vector and hit N for node, and we can see here our starting point is going to be there. And that's going to tell us, and we don't need to ramp because we're going to be entering our material from outside of, or entering the toolpath from outside of our material. And as you can see here, we have our entry point, and that first pass, we're going to be outside of the material, and then we're going to start engaging that material in a north-south motion.
And this is a combination of climb and conventional cutting, but we're not as concerned about this because we're trying to go for the flat surface, and we're not leaving any of that cliff side remaining. And this is really just an efficient cleanup pass. And as Cory was saying before, sometimes when you place your material in your vise, it can kind of be unlevel. So one thing that folks oftentimes do is using parallels underneath your material to make sure that they're sitting parallel and perpendicular to your spoil board or your vise.
Yeah, one other reason I like raster in this instance, is that it gives us a uniform finish at the end. And so we are going to have a slightly different angle of finish on that surface between the raster and the climb cut, but it's going to be consistent across the whole piece, where if you use an offset toolpath in this scenario, you're going to see that offset toolpath, and so you're going to see an inconsistent shape or texture. It will be symmetrical, but it will not be consistent across the entire surface.
Right. The nice thing also is that you have a lot of space for chip evacuation because there's no valley, it's just to surface and level.
Fantastic. All right, well, let's hop into doing a profile toolpath or something similar to the result of a profile toolpath with some slightly different approaches in order to, deal with these materials that are so high in density. And let's go ahead and start with a vector here. We're going to draw a rectangle. It's going to be 11 inches wide and 2.5 inches tall. Perfect. And so a typical profile toolpath, you would see 100% tool engagement with a very shallow depth of cut, right, Sami?
Right. But I think in this case, we're going to try to focus on doing side milling rather than having a very shallow depth of cut, because in this circumstance, we can try to preserve the tool life by making sure we're using the whole tool and not just the bottom edge of it. So yeah. Cory has a really great technique in which we can approach this.
Yeah, so we'll go ahead and here we're going to draw another vector. We're going to change our anchor point to the upper left-hand corner, and we are going to just move this X over 1/4 inch and increase our Y over of 1/2, and then we're going to change this to a 0.375. And we're going to go ahead and create this vector, and what you'll see here is, how did that change? Perfect. What you'll see here is we have over traveled a little bit wider than our final piece, and this is going to allow and make sure we get past the radius of our tool and we get a nice crisp corner. And then from here, what I'm going to do is I'm going to array this vector. So I'm going to move it down. I am going to hit the N button in my hotkey here and make sure that my start point is in either the lower left or lower right hand corner. I want it on these outside vectors. So we'll go ahead and hit escape here, and then we're going to use this array or copy feature. And so we're going to go ahead here, we're going to select this vector. It gives us our vector size, and we're going to do this in a series of 8 different passes or 8 rows, 1 column, and right here is going to be our offset. And so when we do side milling, we're engaging the entire depth of our material with the side of our tool, and this offset is going to dictate how much of that material we engage per pass. And so right now we have it set at 40 thousandths. Depending on your machine, the tooling you're using, you should play with some of these settings, all the way from 10 thousandths up to a 1/16 of an inch, depending on your machine and tooling, could be very achievable. And so we'll go ahead and copy this, and what you'll see here is we get a series now of vectors, and what's important is we select the bottom vector and it's completely outside of our material. And I do this because we want to make sure that we're engaging 40 thousandths of material per pass. And so we're going to go ahead and use these. And while we're here, I'm just going to go ahead and click from the right to the left, which is going to be select anything we touch. I'm going to hold shift and I'm going to unselect our square. And then I'm just going to group these real quick and then move them to their own layer. And we have South Clear as a layer already here. Perfect. We'll go over to our layers section. We'll go ahead and make sure we turn that on. And then while we're here, and before we set any toolpaths, I like to right click, and then I like to copy to layer, North Clear, and then move that up to the north side because it's already there. So I'm going to show the toolpath techniques for just the south side of this material, but you could duplicate these on the north side of the material up here and get good results also. So we're going to go ahead and go back here. We're going to ungroup this back to our groups layer to make sure it stays in that layer. And we're going to create a profile toolpath. And so our profile toolpath, we are going to have a cut depth at 0.51, so all the way through our material into our spoil board. Let's go ahead and select our tool here. I have this 1/4 inch end mill set up here that has a pass depth of 0.51, a feed rate of 100 inches per minute with a spindle speed of 20 thousandths. This is giving us a 5 thousandths of an inch chip. We'll go ahead and select that. We are going to only select this bottom vector, so just that very bottom one. We're going to call this profile. We don't need a ramp in this instance because we're going to be entering at our start point outside of the material, so we don't need to do a ramp or a lead-in. And we're going to go ahead and calculate that. It's going to tell us that we are going to be cutting through our material, which we are aware of, and we're going to get a preview here. And in this instance, I do like to bring up the vectors and the 3D preview at the same time. And then we're going to right click on this toolpath and we're going to duplicate it. And I really like this technique because it kind of numbers them for us. And so we know that we have 8 toolpaths to create, or 8 different vectors. So we're just going to create all 8 of them by doing duplicates. And you'll see that they are all numbered for us now. And all right, so we got these numbered, and so we're going to do this lower one as profile 1, and we'll go ahead and calculate it, and it's going to give us a warning. And then we'll hop into profile 2 here, and we'll just select the second one up and calculate, and then 3, and we'll do the third one, right, Sammy?
Right. So essentially you can see what Cory's doing here is by using these vectors, the distance between the vectors are the step over, or the step over. So how much it goes and overlaps its previous toolpath. Rather than doing that within the toolpath, he's using the vectors to accomplish that.
Yeah, and so I really like to think about CAM as us asking the machine to execute on very specific commands, right? The machines will do what we ask of them. And Vectra products really help us leverage some big efficiencies here. But when it comes to high density materials, I really like to remind myself we are milling, we are not drilling. And so what that means is I want to engage the side of my tool as much as possible. If I am engaging the face of my tool or tip of my tool, I need to really make sure there's a lot of lateral movement that's happening there in order to, get the best tool life and not overheat it and lose our edge and start that process of having a broken bit. So perfect. We have all 8 of those tool paths created now, and we'll go ahead and increase our size of our preview screen here. See if I can get you guys a good angle here of what this is going to look like. And let's go ahead and preview this tool path. And so we're going to start in this upper left hand and come down and then climb along the south side of our material. And you can see every pass we're doing is a 40,000th step over pass at full tool engagement, and it's always a climb cut. And so we are getting very consistent chips, very good chip evacuation, and we're engaging over a ½ inch of the side of that tool, which means we are getting a lot more life out of that tool than if we were just engaging the first 40 thousandths of the tip. Mm-hmm. Cool. One other feature that's really great here in VCarve is if we select all these tool paths, we right click and we click group visible, it puts them all together, and we can minimize and we can rename this to say south. And a little bit more cleanup to help us organize and make sure that we can do the south face and the north face very efficiently.
Organization is really key when you're having this many tool paths. It's definitely a pretty easy thing to organize them by groups and makes it all easier to utilize and export later.
Yeah. So let's imagine that we were holding this in a vise on the right and left sides, and we've faced the south and north sides of our material, and now we want to come back and take care of the east and west. So we might use some additional work holding here from the north and south side of our material, and that way we can work on this, engaging it from the side of our material away from our clamps. And so one thing I like to do here is to draw an oversize or over travel pocketing toolpath. And so let's just go ahead and get a rough dimension here. We're going to have a width of 0.375, and let's do a height of 4.25 and apply. And then I really liked this align to material feature, and so we can, with one button, make sure we're nice and centered. And then we can also hold shift and select this center vector, and then we can go align to outside edge, and boom, this perfect alignment.
My favorite. I always like to also pin it to my dashboard, so I always have it available.
Yeah. And so now here with this vector, let's go ahead and create a pocket toolpath. And we are going to go to a total depth of 0.51. This has us going in 13 passes. We are going to use an offset toolpath, Sami, in this instance. Mm-hmm. Would you use?
Yeah, I would. And then you can select climb or conventional here and make sure that when it's coming up against your final workpiece that we're getting that climb cut.
Yeah. And so you can see here we are going down, and we will be at cut depth when we engage in our north travel. And let's go ahead and move this into its own toolpath area and preview that. And so again, what we're focusing here on is making sure we have great chip evacuation and making sure that when we are coming back along our finished edge, we don't have full tool engagement. We're only engaged in that climb cut.
Absolutely.
Yeah, so here we have a very crisp corner, very similar to the results what you would get with a profile cut by using two different toolpath options.
Right. So by combining these approaches, we can make sure to get your final cut and consider what operation and which approach works for your particular vectors.
All right, well, let's talk about making a counter bore in this material. And so there's a couple different approaches we can take. Again, I'm going to really try as best as I can to do more milling than drilling. And so let's go ahead and let's put a starting point of 6y3 with a diameter of 0.375. And y 1.5. There we go. That looks closer to the center of our material. And what I want to do here is create a helical move. So what we're going to be doing is lateral movement as we go down into our material. And the goal here is to make it a 1/4 inch down. And so we're going to actually do a profile toolpath to 0.25 inches. We're going to select a new tool here. I'm going to select my ZRN upcut. This has a pass depth of 0.04. Right now I'm not too concerned over the step over as I am the pass depth. Also our feeds and speeds here have our chip load at about 2.5 thousandths. I don't know if this is an achievable feed rate at this size, and so what I'm going to do is I'm going to drop this down to 40 inches per minute. And therefore, I'm also going to drop my tool RPM down to about 9,000. And so that's going to be a more achievable feed and speed for this size vector, right, Sami?
Yeah, definitely considering that the lateral movements, it's not going to be able to get up to that fast, and also to consider the type of chips that you're making and the heat distribution.
Yeah, and so I do want to ramp this toolpath, and I want to ramp it at about the diameter times 3, or just under pi. And so it's a 1/4 inch diameter, and so that means our ramp distance is 0.75. And I'm going to call this CB1 because this is actually our CB clear, because this is going to be the area where we clear the area to create our counter bore. And so let's go ahead and calculate this. Perfect. We'll reset our preview. And what I want to show you here is that we are moving laterally as we go down to that cut depth. And so we are going to be engaging the side of our tool as it goes down into the material. And this preview is a little bit slow because our feed rate's a little bit slow. With our series machines, I'm usually in the hundreds of inches per minute when it comes to feed rates, and so the Vectric preview can seem very fast, because it is. And when we slow our machine down to a more achievable feed rate, it gives us a little better preview of what it's actually going to look like when we're doing those machining practices, right, Sami?
Yeah, you have to consider the limitations of that, your machine imposes versus also the limitations the vectors impose, and also the simulation versus actual. So I do encourage you to also record your times, and then check your time predictions in your toolpath to see how accurate that is, and you can change the scale ratio, and it will give you more accurate prediction times in the future.
Yeah. So what we're doing here is we're creating a hole or a counter bore, and so that way the rest of the rest of our counter bore, which is going to be to 1 inch in diameter, we can engage a 1/4 inch of our tool instead of that 40,000th tip of our tool. And so right now we are just engaging the tip as we do these helical moves down into our material. But once we've created this cavity, we're going to set up an offset toolpath where we actually go down to the 0.25 as our depth of cut and have a very small step over as we go wider and wider. So let's do that. So we're going to go ahead and draw another circle here at the center of our workpiece. This circle is going to have a diameter of 1 inch. And we're going to go ahead and we're going to create another pocket toolpath for this. We're going to have a cut depth of 0.25 inches. We're going to go ahead and select a different tool. We're going to select this tool here with a pass depth of 0.25 inches. 0.25. I sometimes put twice those points, and we're going to do a step over of 0.03. And so this is just about a 12% step over. And again, we're going to slow our feed rate down and our spindle speed down because we want achievable feeds and speeds when it comes to setting up our machine and to get that proper chip. We want to calculate these chips with feed rates that we can achieve, right, Sami?
Absolutely. And with the interior of a circle, it's going to be very different than the exterior of a rectangle.
Yeah. And so we're going to do an offset toolpath. So that's going to start in the center of our work. And we're going to do climb. We don't need to do any ramping moves because essentially we've cleared that material away already. And let's go ahead and calculate. And what you'll see here is we're going to enter that material from the middle and we're going to slowly work our way out. And chip evacuation being a huge goal along with tool engagement. So let's go ahead and see this. And so we are working our way out to that 1-inch counterbore, and we're using a lot of the face of that tool, and we have plenty of room for those chips to get out and keep that tool cool.
Right. And you can always use a little encouragement with some compressed air or something like that.
Yeah, so let's go ahead and finish off this counterbore now and go all the way down. So I would now do a third toolpath with this inside vector. And so what we're going to do is we're going to do another profile toolpath. We're going to start at a 0.25-inch depth and go to a 0.26, so 10 thousandths deeper than our material. Let's go ahead and make sure we have the right tool selected here. We have a pass depth of 40 thousandths. Perfect. And we have 9,000 with a 40.
Okay, so
Hi, everyone.
Go ahead, Cory.
Yeah, we apologize for the technical difficulty there. For some reason, our presentation just cut out. So I'm going to talk a little bit while maybe, Sami, you can try to pull up a secondary window with that presentation where we left off. So what we were doing there is we were creating that counterbore, and we were using that helical move into the drill, and then we were machining the counterbore, and then we were going to use another helical move to go all the way through the material. And the advantage to making the counterbore before we go all the way through the material is we are giving more room at the top of our flutes for those chips to evacuate through that deep cut.
Right, and so I think we're about to go into also talking about the chamfer toolpath as well. So I'm just going to go ahead and just give it a short example of that here. So we have, as an alternative to doing a counterboard, doing the countersink, which is a perfectly nice bevel for your screw head to sit in, making sure to accommodate for the angle of the screw head, knowing what that angle is, and making sure that your router bit matches here. So let's go ahead and do a chamfer toolpath. I'm going to select my vector here, and you can see the direction. It gives me an arrows, and I can, switch those outside, inside, slope upward, but we want just kind of the traditional, here, just making sure our sound is good, everyone's back. Okay, good. Just double checking. Thanks everyone for your patience there. So we're just going to go ahead and so you can change your width of the chamfer or the cut depth, and it will adjust based on the bit you've selected. So if it's a 60 or a 90, those will change. So I can say my cut width is 0.2. We'll just calculate and preview that visible toolpath here. So we also want to accommodate for, we'll just say that we have another helical toolpath here in the center. We'll just say 0.5 as an example. And I'm just going to do an interior profile. make sure it cuts to the full depth. So I can just do point Z, or just Z because it'll reference the material thickness I entered in my job setup. I'm going to use my 1/4 inch tool, and I'm just going to double check my settings here. So I'm going to, this is kind of more my plywood setting, so I'm going to reduce this to 40 inches per minute and a plunge rate of 30 inches. And, you know, we're just to double check that our chip load is going to be reduced here to a reasonable size. Always checking this, so we say okay. And just go ahead and calculate that. So I double check that it's on the inside rather than the outside. And I'm going to run this before my chamfer toolpath, because then if I run that, it will clear out all the space I need for my chamfer here. And I would, you know, maybe make an adjustment here so this is meeting up better.
Yeah, and this is a great thing about the Vectric preview with your toolpaths, is you get an instant visual feedback there. And, you know, that's so powerful when we talk about correcting mistakes before they're on the finished part.
Yeah. And someone just pointed out that Cory has this tool set up for this material. I have 4 computers. So, you know, this is the example. And, you know, that is a big thing about trying to keep your tool library set up and synced across all your computers. So I have my stream computer, my Mac, the controller computer for the bench shop, and the controller computer for the machine at the shop. So making sure that those are all synced, and when you're sending files back and forth, to make sure that it holds that information is important.
Yeah, but more importantly, I think, Sami, understanding what knobs in the tool database there that we want to adjust and where our baselines are, because even though we're in a material we are aware of and we know some of the settings, reviewing those and making sure they're perfect for the toolpath vectors that you're trying to create is always something that I'm going to encourage people as a double check. You know, the better diligence we can have in the CAM area of our toolpath creation, the easier it is to be an operator.
Right. So I do have a quick video I'm just going to play, and we're going to just talk over it kind of. It's the compilation of setting up and running the part, so I can kind of show you about how I did this work holding fixture and how I kind of got set up. Yes, you know, an enclosure would have been far more ideal, dust collection setup, but, you know, kind of the dust boot can interact, you know, with the sharp edges of aluminum, so I opted not to do that, especially for better filming so you could see it. So I used the 6061 aluminum just from McMaster. Here I'm just showing you to show kind of what it looked like before machining. It's extruded, so it's pretty consistent, but a little rough around the edges, which is why we want to clean it up. And yeah, so here I'm going to use our touch plate to pocket out my plywood. So I have a piece of plywood that's screwed to my MDF spoil board, and I'm going to just use the bit that I had in, which was a 3/8 upcut here, and I'm going to set my 0 to the jig itself. So I kind of changed it to what we had the original 0 setup, but you can kind of just adjust that on the fly as you need to, right? So then I'm setting my Z to the spoil board bed, and I'm going to go ahead and pocket out the size of the material that I am going, the aluminum itself, with some dog fillets, dog bone fillets.
Dog bone fillets in the corner. Yeah, no, this is a great example of Sami, you know, taking some of these techniques and applying them to her preferred zeroing and work holding patterns, and really leveraging those techniques with what she considers is the typical workflow.
Right, and so that's also a big thing about communication between someone who's programming the toolpaths and somebody who's running them. So because Cory and I do both, you know, we can kind of adjust those files to how we would like, but communicating that when you're sending files from the office to the shop, making sure that that communication is really clear is important. So here I'm just doing a pressure fit. I had thought about doing blue tape inside of my little pressure fit jig and then blue tape on the bottom of the aluminum. But when I did this test fit, it kind of just was so snug, I knew it wasn't going to go anywhere. Here's the bit that I used, 1/4 inch. This is with the ZR and coating. I was trying to get it to focus there. So now I'm going to set my 0 to the material surface of the aluminum. My XY is still set to the corner of my jig though, because that's kind of just what I chose to do. So I'll reset the Z to the material height. And we're going to start out with our leveling. Ooh, I got some bright sun coming in here.
Surfacing, yeah. So look at that surface finish there. And so phenomenal chip evacuation. If you wanted to use any compressed air, I also have used wedges of different sorts and just blowing that air into a wedge for collecting the chips. That works really well to try to keep your floor as clean as possible. Yeah, this looks really nice.
I have a really fun enclosure design that I haven't had a weekend to build yet. But it's like a tiny, because I've always wanted to build a tiny house, but I don't have space for a tiny house build, so I'm going to build a tiny house for the CNC machine. So stay tuned.
Oh, that's fantastic.
So here's the first, this is the east side. So this is the pocket toolpath that has the smaller pass step and that step over here. So just because it's really nice that you have that blue edge, you can really see kind of the material that's being removed. Mm-hmm. And we will end up cutting into the plywood here because the aluminum is sitting into that pressure fit here. And I do add the second clamp on the other side once I have this edge relieved, because there will be no pressure on the east side of the material at that point.
Yeah.
Right.
Yeah, and so this is without any lubrication. Whether it's compressed air or lubrication, if they encourage chip evacuation and your work holding fixture, can handle it over time, I am always a fan of increasing your ability to have good chip evacuation. But if this were a jig that you wanted to use over and over again, lubrication wouldn't be an ideal scenario unless you change the material of the jig from plywood to something like another metal or plastic.
Yeah, HDPE or something is a very common choice for that, right? Someone's asking if Avid CNC machines are kits. Yes, they are kits. And that kind of gives you the added value of having a really high quality machine at a more affordable price. We're all about really high quality machines for really exceptional value. And here's that front edge cut here. I kind of wanted to, I should have made that profile a little bit taller so I wasn't cutting it on the right movement and only on the back, but it does kind of come back to clean that up. Another added value of having, here's the counterbore. I know I'm jumping back and forth here, but this is a nice shot. Of building your own machine?
Yeah, I was going to say, these lateral moves as we plunge down into the material, it's one of the biggest takeaways if you want to machine aluminum accurately with a router, is we need to have that lateral movement as we go into the material. And you can see here exactly why. It's because it allows those chips to get out and away from our tooling.
Yeah, look at those chips. Those chips came out perfectly, really nice. And I was really happy with the results of that. Here you can see, I'll hold this up a little bit for you.
Yeah, and then we're going all the way down, and that counterboard area is actually really allowing those chips to escape. And so this is a great technique, even if you don't need the counterbore for a bolt, if you're going to be bolting from the other side, and you can just increase that counterbore to a little bit larger than your tool, you're going to increase your ability for chip evacuation. And whether it's compressed air, lubrication, or really good cam techniques, when machining these types of high-density materials, chip load and chip evacuation should be exactly what is on the front of your mind when you're in the cam space of your CAD/CAM workflow.
Right. Yeah, so one other thought I had about the kit question was that, it's like big Legos. It's so fun to build. Also, you'll know your machine so far more intimately than perhaps somebody who might have had a machine delivered, right? You're able to understand the fundamentals of why it works the way it does. You know, we all kind of understand the XYZ geometry class, Cartesian coordinates. But when it comes to understanding, like, oh, I'm putting this X plus sensor here and this X minus sensor here, I can understand why it's stopping at a certain point, or what those limitations are. I can replace all the parts myself. We have a support team you can call, and they'll, you know, Brian and Cory are happy to help you with that. So thank you all so much, and we really appreciate, let me see if there's any more last minute questions here.
Yeah, there was a question on climb versus conventional milling, and I think this is a really good question. I think typically with high density materials, I'm going to reach for a climb technique if I am really concerned about the finish quality. If I'm less concerned about the finish quality, I'm going to either use a raster toolpath if it's a pocket, and I can do a little bit of both. But even if it's just a profile or any other type of non-visual element, I don't think conventional is gonna be that bad of an option.
Right. Awesome. Well, I hope we've inspired all of you to go ahead and try out some aluminum or brass or non-ferrous metal machining. Let us know how that goes. Feel free to reach out to our support team, support@avidcnc.com, or find us on Instagram. We'll be there to kind of celebrate your chips and your cutting. Happy making, and I hope you all enjoy the next talk. I believe it's the final talk with Michael, right? So thanks everyone, and we'll see you all soon.
Thank you.
Bye.